I'm making up the sleeve to sit around the ER 25 collet that I've got on a 16mm shaft. These are usually pretty accurately made, but I will chuck it up and just check to see how accurate. And then this goes threaded through here, and I'll Loctite that on. And I've got to just make this a little bit longer than it needs. I've checked on the spindle and see the length that I need. I've made this oversize. It's 1mm oversize to allow for the thing, when it's being glued on, not being quite straight, or me not having turned it quite straight in the first place. So that's the next job. I'll turn that off. Before trying to fit anything to the spindle, it's a good idea, especially if it's going to be using a pre-machined part like this, to see how accurate it is. And the first part of this exercise is to set the chuck up to get that running as true as possible. I have got a collet chuck that I can fit in here, which is much the same accuracy as this. Fortunately, this is an adjustable chuck, and there are, just open this back up again, on the side there are adjustment screws, and you slacken the front screws off and then turn the adjustment screws until it becomes as near perfect as you can get it. And I think that's as good as I can get this. You can see the needle is less than 0.05 of a millimetre, so that's as accurate as I could ever get with a 3-jaw chuck. Now the thing to do is to check the machine surface here and the machine surface here, because I might be relying on this for doing machining and to hold it, and I need to know whether the inside cone is correct or not, and it might need correcting. So let's try this first, and I suspect that this will have a bit of run out on it. It does. It's about get that set on the 0. Sorry, 0.03 of a millimetre. Which is not very good, really, to be honest, especially done with a machine that's as capable as the one that they use for grinding this. So I'll now move this back and try and get it set up for the cone. Well, the cone's not too bad. That's 0.01 rather. Yeah, 0.01. Maybe a little bit more, 0.015. But that's not too bad. I've seen them a lot worse than that. So the next thing to do is to pop a collet in there and a dowel pin. I'm turning down the collet to fit in the spindle. I've got one end supported by a 10mm brass pin with a centre drilled carefully into it. The other end is in the chuck, where I've accurately centred the chuck. I've just nearly got to the end of the thread cutting. It gets on to about 3/4 of the way down. So I've just got to run this down. More spring passes, very light cuts. Yep, that's pretty close. Just run it down a couple more times with a light cut and then that'll be it, finished. Yeah, that's going to be enough. It doesn't screw right up to the end anyway. That's it. Hooray! That's another job done. And I can check how that all fits together on the body of the milling machine. I'll perhaps move down there now. I've now transferred to the lathe. And if I just check here, there's almost no run out. I'll just move the needle a bit further over. There's almost no run out at that point there, and it's centered on the 10mm collet that I used before. So if I move this up to the cone area and just check the measurement there, again very little run out. I didn't think there would be very much, but that's slightly better than I thought it would be. So I need to come up here now and just check the pin that's in the collet chuck. And what that's telling me is that there is a 0.02, 0.03 of a millimetre error in the collet. I'm just carrying out some accuracy checks on the milling spindle, And the first thing to do is to check on the original to see how accurate the spindle is. Now I would have expected this to be pretty accurate. I set the dial gauge up and you can see that the original spindle is extremely accurate. The needle barely moves. And it is definitely making contact. You can just see if I spin that round faster, you can just see there's a bit of movement. So that is just amazingly good. It's almost no error, and that's after 100 years. I guess they can show some of the people with fancy CNC equipment a thing or two about accuracy. That is amazing. Having established that the inside of the spindle is pretty good, I can now check to see how much less accurate it is, having inserted the adapter that I've made. And there was a little error inherent in the collets right from the start, so I've now set up the dial indicator to indicate off the inside of the ER collet chuck, and you can see that's really quite accurate now. That's 0.02 of a millimetre, so it's introduced an error into the measurement which has come from this inside of this chuck, which I'm not going to remove, but it's not quite as accurate as it was originally, but it's still pretty good and certainly adequate for doing normal milling operations. So the next job is to chuck up and put a pin in. I put the pin in, and as you can see it's about 0.03 millimeters, 0.035 maybe. So I think I'm happy with that. I'm not going to get it any better unless I redid the inside face of the collet chuck, and I'm not going to be doing that. So that's that done. And the other thing I'm going to try and do is I'll try and make a drill collet. So this is a standard taper for drill chucks. I'll try machining this down. I can see it's been threaded and looks like it's been turned and everything, so should be able to turn that, I think. It may be pretty hard, but we'll see anyway. And it's got centres at both ends. Not a centre at this end, rather a centre at that end. While I've got everything set up in the lathe, and I've checked the chuck recently, I thought I'd just put the converted R8 collet that I'd made up and changed to one to fit this, which is a 4 NS, and this came with a B12 taper, and I've ordered a chuck for it, and this is the accuracy that I've managed to turn this. It's not ground, so it's 0.03, 0.02 and a half, I don't know, 0.03 say, which is not too bad, and I dare say the chuck will have some run out in it as well, so maybe I can just adjust where that run out is when I put the chuck on. I can't do much to change this now. I'm certainly not going to regrind this, but that's as accurately made as I could do just by turning this very hard steel. I think the problem with turning this as it emerged as I was doing it was the keyway. It disrupts the cutter as it's going around, and however small a cut you take, it tends to jump as it goes over this, so it's not quite as accurate as it ought to be. This is very hard steel, but it is possible to turn it, and the best turning tool for any of this sort of nasty steel is one of these. They're PWLNR, and it's a 1616H08 tool holder. I've set up the drill spindle, and just by way of comparison, with exactly the same settings for all the clamps and everything that I had before, and that's within 0.002, so that's pretty accurate. So I could put a drill chuck in there and know that it'll drill nice and centric. So I'm pleased with that. The ER collet, it's not unusual to have problems with ER collets running slightly out, and I only ever manage to get them perfect when I regrind the inside of them and fit a super accurate nut, but I think that should be adequate enough for using for this purpose. Perhaps I might just show you the latest part of this now. I've mounted the motor, but I haven't got a drive belt yet. Let's move this round. I can show you where I've got to. What I've done is, on the back of the mill there are two screws in here. Let's move out a little bit. There are two screws in here, one there and one there, and that holds a bar that I've put in, so I haven't drilled any extra holes. The only thing I did was, as the face of this wasn't flush with the face of where this bar is on the underneath, so I milled that off so that it was flat. But apart from that, that's all the only alteration I've had to do. I've still got my locking levers here, and everything else is the same. And the belt obviously goes through to the motor on there. I think slight difficulty in getting a belt the right size, the right short. They're very short belts, and I need to have a fairly thickish one. So I'll have a trawl around the internet and see if I can find one. But that's where I'm up to with that. The method of applying power to the main shaft has varied from time to time, and I've looked at various photographs, and it shows several different arrangements. It's also interesting to note the grinding attachment, which has a pulley built into it, and which is driven directly to the spindle. This first photograph shows the 1901 catalogue, with it having clearly 45-degree helical gearing, which is known as cross gearing. And on the page after the attachment was shown, some examples of gears that were made on the lathe using the milling attachment, and using the attachment that allows for long helical gears. The last of these shows an arrangement with a worm gear, which drives a larger wheel on the spindle, and clearly this is revolving at a much slower speed. The worm gear looks like a 2-start thread, so it's something like a 1 to 20 reduction, something of that sort, and would be only useful for having very low speed. I'm now going to demonstrate how easy it is to swap out items on here. So if I want to alter the drive arrangement, so I just take this off first. That's taken the collet out. This has one screw that tightens up, and it doesn't need to be done up very tight, it just needs to be done up moderately tight. And I hadn't discovered until when I was looking at this a little bit more carefully where that screw is there. And you may just be able to pick out here where the tip of my screwdriver is. There's a faint circle where that brass plug sits, and it's adjusted by turning this screw in, and the screw, I don't know, probably goes down about half the way through, and then there's a closely fitting brass plug which is threaded, so that when you screw the screw in, you only have to give it a minute turn and it locks the threads. Very clever arrangement, but of course takes time to make up. And you probably notice as well on here there are holes for applying a spanner to it. Oh, and you can see the 19 for the same part number that I had on all of them stamped. Driving wheel on the back here is keyed, and I've had to make a key because I hadn't got a key that was the right size. Okay, it goes in like that, and it's actually quite a nice moderately tight fit, but I can get it out reasonably easily. There. So that's that wheel, and these two adjustable stops here that tighten onto this, the plug in under here onto this surface, are a bit of a nuisance because they do get in the way of making a gear wheel up. Now I've bought gears, these are from HPC, and they're helical cross gears, so they're exactly the same as in the catalogue, which I showed earlier. So if I get these on the same way into the keyway, there we go. Now, for the drive for this, there's another gear that goes across the top, and where previously I had the motorised bracket hanging off here, I can't fit that in the same way, so I'm fitting this out exactly as the original was done, but the block I've made up here is not identical because I haven't actually got any dimensions of an original to copy, so that needs a shim underneath it, which is an adjustment for the depthing of the gear. And that goes in the same hole that the bracket is, so I haven't had to drill any extra holes in the milling attachment. Righty-ho, so that's that. And this is the way that this works. Now, perhaps I might put this in just so that you can see that that still will fit into there. I've probably got a little bit too much free play in the gears here, but it's better that than being too tight. But I'm probably unlikely to use it, but I did it because it was just interesting to know. This gear that goes in I showed you fitting first has to sit over the centre of here, which is why that has to be a certain distance from the edge here, and the size of this wheel is limited. So what I've got is 14 teeth on this wheel and 28 teeth on this wheel, which are 1.5 module, and they're standard out of the catalogue, and I've just done a little machining on here. I bored out the inside of it to fit a 1/2 inch shaft, and the 1/2 inch shaft runs in oilite bushes with little oilers in here. On this one I had to bore out quite a bit because there's a 20mm shaft that goes through it, but it didn't prove to be a problem. Now on the original, the gearing is on belts running up to an overhead drive, and it would be a neat arrangement if I had an overhead drive, but I don't. And I couldn't think of an easy way without destroying part of this to mount the electric motor to drive it. I suppose probably the neatest way to do would have been to mount the electric motor here with it using a connector like a CNC drive has. Now the one thing I've got against this is that you've got a mechanical disadvantage when you're driving a small wheel driving a large wheel, which is inevitably what you've got. So that's a ratio going down from 1 to 2, and if you wanted to have an improved mechanical advantage, it should be the other way around. It's much easier to turn that onto that than it is the other way around. And the same goes for a worm. The worm can only be driven from this direction. I suppose you could say with a worm it's the opposite. The worm is driven from this direction, and you couldn't turn a worm by turning this wheel at all. But I say at all, it's very rare that you get anything that works. I made a clock that's got a worm gear that's driven by a wheel, but it's very unusual. It's mechanically very inefficient. So I was quite pleased when I did all that, because it looks just like the original, only I haven't got any drawing of the original. All I've got are them fuzzy photographs, and mine differs from the photographs because it's got these two adjusters on the side, and I didn't want to do away with those, and I couldn't therefore take a bracket down here and screw it into the face. So I'm happy enough to use the direct belt drive on an electric motor. I think that's the best arrangement. So my next thing to do is to set this up on the lathe as soon as the parts have come that I've ordered, and I can then do a little bit of machining and a little bit of drilling. I'm quite happy with the accuracy I've got now. It seems nice and rigid, and I'd be very interested to see how it works. Right, this is the attachment with everything built in. Let's lock that. I've got a 20 amp 24 volt power supply sitting underneath the camera, and that feeds round to this wire here, and I've got a 60 volt motor controller, 20 amp, It's 9 to 60 volt, shall I say, motor controller. It comes with a potentiometer to adjust the speed, and I've checked the speed, and it runs up to, shall I say, 1500 RPM. It's nice and quiet. That's 500, 1000, 1500. It's just resonating a little bit on this tabletop, but it's nice and quiet. I've run it for 20 minutes and it only heated up by 10 degrees, so it's just very slightly warm on the outside here. I'm quite happy that it runs on a very thin film of oil, and will need oiling after every run. The little oiling nipple in here. And the screw at the front. I don't suppose this is going to take very much, but I will just put some in to see. Oh yes, that didn't take much at all. And I think that this sits permanently in a film of oil and uses almost none of it while it's running. I'll just move this down so that you can see it from around here. And that's effectively maximum speed at 1500 RPM. And I did manage to tighten up the tolerance on the spindle, so that it's now 0.02 of a millimetre rather than 0.035 or 0.04. I did that by grinding the slopes on the inside here. So that is as good as I could hope for. It doesn't get hot, it runs nice and smooth, and there's plenty of power in this motor. It's very difficult to stop it with your hand, so there's plenty of torque there, which is what I hoped it would be. And even running at low speed, there's still quite a bit of torque. After all, this is intended for a scooter which has got an application that needs plenty of torque. So I now put this in the lathe and run some operations on it and see how it fares. The first job to do when setting this up on the lathe is to make sure that its height is aligned perfectly with the centre of the chuck, particularly in drilling operations. And it's actually simpler than you might think. If you just put in to an accurately centered chuck a point and a similar matching point in the chuck in the milling spindle, then that achieves the same height by just turning the handle at the top. And when I was first setting this up, I found that I was ending up with this. In order to get this aligned, I needed an extension here on the lead screw. Not a problem, I just made an extension piece, just knocked that up, so that anything that I measure from here over is giving me an offset from the centre. And again, that's just simply by visually looking at it, and probably best to use an eyepiece when doing it. Now, the way I have this set up, the slide is set back at the furthest possible point, so I've got 4 inches of travel in this direction, which means I can drill 4 inches away from the centre line of the chuck, So therefore an 8-inch circle I could drill holes 8 inches apart. The simplest way to see how far out I need to come, to measure how far out I come, is to measure this distance. I set it up on the digital scale. I might devise some method of measuring it which is more direct in the future, but this is just for the moment. So let's just check what this is at the moment. I think it was 65.24. So if I make a hole 10 millimeters further out, do 4 holes 10 millimeters either side and up and down, that wants to come down to 55.24. That's 55.24, so that's 10. Now I can set this up to drill. I can take this out of the chuck. I probably ought to just lock the screw on there so I don't inadvertently move its position. Right, so that's locked. Take this out of here. I'll do a series of holes with a centre drill. Over here is the arrangement that I use for indexing the holes. I've got a plate mounted on the collet closer tube and it's fixed to the top of the gearbox, and I've set it up with divisions. I've on a 24 hole division, and I've got them marked so that I can see where the quarters are. So I'll move it each time a quarter. So I just put a little bit of oil in the spindle. I'm set up now, ready to do the drilling. Just tuck that out of the way so it doesn't get caught up. Just make sure that that is locked tight. Yeah, and that's locked. That's locked. Okay. Change the drill and put in a level 3mm, I think. Now that's the first operation, just to show how to drill into the face of something by indexing it. If I just take that out of the chuck, I can show you. And these are the holes that it's drilled, and that's 20mm. So it's a nice accurate way of doing it, and a fairly simple solution. I think the next job will be to drill crosswise through a shaft. I think if we put something in here and literally just drill straight through, that will be on the centre height because we set it that way, and it's quite a handy thing being able to do that. So that's the next job. I'll get that set up first. This is drilling through 1/2 inch stainless steel. I've got a spotting drill, so I don't need to pre-drill it with a centre drill. I haven't done this before, so let's hope this works alright. See, immediately I've got a problem. I should now be in a position to hopefully drill this. So let's give it a try. There we go, drilled through that without any trouble. I probably had the drill running a little bit too fast to start with. It doesn't seem to have moved while it's done that, and drilled it nicely in the middle. So that's drilling from the side through something like that. The way that this is set up is very different from how I set up the milling attachment for the first lot of drilling. I'll just turn this off. Wrong plug. Really, this is rather too long between here and here, and I could easily, so if I use the ER collet chuck, I could probably drill considerably closer in that position. So yeah, I think it's all a matter of trying it and seeing how I get on. The handle getting in the way of the closing collet tube. Anyway, it has done it. I need to do a bit of practice on doing other things. It's certainly a robust, strong method, and the power of the electric motor is fine. The belts weren't slipping there. It was just slipping where I'd got it chucked in with insufficient force. I've set up to cut a keyway in a piece of EN9 steel, which is basically a high carbon steel that can be hardened, and I've set it up for, it's a 4mm diameter cutter, and I'm trying to do this in one cut. I haven't done this before, so we'll see how we go. It's 1.5mm deep, and I just have to hope I don't break the cutter, and I need to get the cutting speed about right, which is going to be trial and error. So I'm saying we hope we don't break anything, but we'll see. I'll just cut about 10mm. That looks pretty good. That looks as if it's going to be okay. Just move that up so you can see it. So that did a 1.5 deep cut. I would have probably done a 2mm deep cut without any trouble. So yeah, I don't need to do that again, I don't think. That just to give you an idea of what this is capable of. This is a very, very stiff cutter, a very stiff spindle, so it cuts very well. I set up to do milling flats on a piece of EN9. This is a 10mm cutter, and I'll just have to experiment a little bit to get the cut deep enough, and then I'll flip it over and do a cut 90 degrees and give you an idea of how this can cope with it. I've not done this before. This is for trial and error right now. So let's just turn this on. Seems to cut that easily. just taking a slightly deeper cut. Should have made a sharp joint there. It has. That's finished milling that now, and you can see it's produced a very nice square. It's the sort of thing you'd use for winding squares. Yep, I'm happy with that. That copes with that easily. There's no chance of stalling the cutter or anything like that. So that's yet another job I can do with this. I'll probably set up to do one more operation and then I'll call it a day. I've set up to be able to cut a clock wheel with a clock cutter. This is 75mm in diameter, but it has shown that there is a limitation on the mill, which is the overall height that this can reach up to. It's fairly constrained, and I could do about an 80mm diameter wheel, and then it starts becoming a bit of a problem. I think the answer is, if I just move over here, and you'll see this is getting close to here to the adjustment for height. So I can go up a bit more, but that's about it. What I think I'm going to do is I'll make up two blocks to fit under the top that act like riser blocks, another 25mm high, so that it can go up 25mm more. It won't affect anything that I've made here, and it will just give me a bit more flexibility in the overall height I've got. I did wonder if that was going to be a problem, but anyway, that's the way I can cut gears, and that would get me up to a wheel of 5 inches or so in diameter, which is fine. I don't think I could expect to do much more than that. And if you see that this is a 5-inch chuck, and it would only just go down the past the top here, just clear that. So if you had a wheel 5 inches in diameter, that would be the maximum. So I need to be able to raise the height of this a little bit more, and then it would be fine. There's usually not too much force involved in cutting gear wheel teeth unless they're cut in cast iron, and I don't want to cut this now. If you're wondering why I'm not cutting it, I just don't want brass sprayed all over everything. So that's the sort of explanation of what the limitations are and what the benefits are of this particular milling attachment. I'm very, very pleased with it, and I'm certainly glad I've got it.